So good morning to all of you, and welcome to the first IEEE International Conference on Blockchain and Cryptocurrency. I am Sondip Chakraborty, an assistant professor at IIT Kharagpur, India. So I'll be chairing this session. This is the first session of the conference. So we have 3 papers in this conference. I will request all the authors to be on time. So we have 25 minutes for each paper, including the question and answer session. So our first paper in this session is RouteChain towards blockchain-based secure efficient BGP routing. So this paper will be presented by Aziz Mohsen from University of Central Florida, USA. So Aziz is an associate professor at University of Central Florida. So before joining UCF in 2017, he was an assistant professor at SUNY Buffalo. He obtained his PhD from the University of Minnesota and spent several years in the industry. So his research interest is computer security and privacy. So over to Aziz.
Are we good? Okay, so first there will be a background problem statement, then challenges, needs, and motivations, like what is offered by blockchains, what we actually need for our system, and then I will talk about the key design choices we make for RouteChain. Then I'll talk about full design and analysis, evaluation results, conclusions, and questions and answers if you have any questions. And so a little bit background if you are not really into networking. The internet is a bunch of autonomous systems. The autonomous system basically is a collection of routers controlled by an ISP, organization, entity, whatever you want to call it. And those ASs define policies on the internet as far as relationships between different organizations for networking. ASs enable 2 types of routing, intra-AS routing within the AS, that is to say, for example, routing within SK Telecom, and then that is inter-AS routing, that is communication within, say, for example, SK Telecom, and then intra-AS routing that is between different ASs. And of course, ASs are assigned, their unique numbers assigned by a ring. And so typically an AS would be, as I said, a bunch of routers defined by a name, and then those routers within the AS have their links, determining the communication patterns, and then across ASs there's also as well the communication between them. And so the BGP is the de facto standard for routing on the internet today. It uses defined relationships among ASs, so based on peering relationships. And for reachability purposes, BGP speakers or routers would announce prefixes that are reachable from within that BGP speaker. And each AS owns a subset of network prefixes that controls, for example, /20, 24, /16, and so forth. That can announce on its behalf of itself and propagate to others to announce reachability on behalf of it. And so typically, say, for example, if we have an AS 300 in the lower part of this figure, then AS 300 controls /8 defined as follows. And so it can actually announces that, well, this prefix is reachable from me, announce it to its peers or its immediate connections based on relationships. And then, say, for example, A wants to send traffic to AS 300. It would push it to whichever is favorable route, either through C, D to E, or either B to E. That is how the internet works today. Now, the issue that we have with BGP, what we define as BGP problems, is that there is a very weak trust model in the sense that security boundaries are not very well defined, that anybody can actually claim whatever he want to claim on the internet. It's vulnerable basically to BGP attacks, basically hijacking, whether it is partial hijacking, stating that, I have a favorable route to a given destination, or complete hijacking by claiming the whole path to a given destination. And so the BGP problem here is demonstrated. So again, with the previous example, let's say, for example, we have a legitimate mining pool server and your favorite application of cryptocurrency. And then you have a miner. The miner wants to push some information to the mining pool server. Then it would use a well-defined route over the BGP. Now let's assume that there is a malicious server on the internet that would want to basically, or a malicious player on the internet that wants to claim the legitimate mining pool server. all that need to do is just announce that the original IP address 1112 is reachable from him, and then if it is actually happen to be a favorable destination, then it will be able to route all the traffic to it. And so that's what we call BGP hijacking. Now, a solution to this problem is very well understood in the literature, and it is very useless, I would say. So basically, the challenges with existing solutions, such as solutions that use RPKI, which introduce a central route assigning authority, is that really it is cumbersome and operators really hate it. ASs typically are unwilling to trust a single point of trust that can perhaps have a lot of leverage on them. And so we need a solution that can be incrementally deployable and backward compatible. We want to have a consensus over false split gas before they are converged into the system, into routing tables. That is to say, we want to have a very fast consensus algorithm for the announcements, and we want to implement it in a centralized manner as much as possible. And so what we want and what we're given, so what we want to establish a shared database of routing information that is verifiable by all peers. We want to develop a consensus over the state of this database to allow transparent and consistent viewing among nodes. And what we are given is quite limited options. So we have peer-to-peer architecture, that is ASs, states that change by the BGP announcements that I mentioned earlier, by announcing prefixes. And we have peers of the same type and conflicting interests, that is, say, ASs. Among them, there could be a good, there could be a bad, there could be a conflicted. And so we want to do that efficiently and quickly. That's the title. So what do we get, actually, by just applying a standard blockchain system on this? We will get augmented consensus in peer-to-peer settings. We will get to maintain a single ledger of routes of plotted size, of large size, depending on the number of announcements that each AS does. We will have actually a route visibility to all. Given that we have a single ledger, then anybody can see whatever is in that ledger. It's public. We will have a swift attack detection in the sense that everything is a single place. Then you can actually detect it. Detect like any piece. And then we will have provenance without violating structural properties. Maybe we will have a slow consensus by design for most of the existing consensus algorithms, such as proof of work and PBFT. And so in social media terms, what we will have is that we will have some good properties, such as the consensus being over peer-to-peer settings, that we will have route visibility, we will have also swift attack detection. We will have something that is really less amazing, such as maintaining a single ledger of routes, which is with bloated size, so that's very hard to maintain. We will have something that is really meh, such as provenance without violating structural modalities, in the sense that those modalities are actually associated with relationships with communities. And so we will have also a slow consensus, which is really quite bad in the sense that you want to do things in a quite fast fashion that any anomalies can be detected. And so our solution to the problem is to get a compromise around all of those issues, not to achieve the best among them. We do the first one with almost peer-to-peer multiple ledgers that can be deployed respecting the structural properties of the system, called communities. We will want to have a swift detection. Still, we will have to go some penalties to do with latency on the network. And we want to have a fast consensus in the sense that we utilize a faster consensus algorithm that is more appropriate to the system settings that we have. And so this is what we call RouteChain. So in RouteChain, we have two key ideas. The first key idea is that we partition the ASs within geographical proximities into communities. And as such, we will have subgroup blockchain systems. Those subgroup blockchain systems or local chains will basically keep track of routes of all ASs within that group. And we will have a single global blockchain that is of moderate size that only has route changes confirmations across different communities. And so in this setting that we have here, if we have like AS1 through AS4, and this is your entire system, and supposedly AS1 and AS2 are within the same geographical proximity, we can group them into the same structure, and then we group the others which are supposedly within the same geographical proximity with each other. And those actually, with their announcements, will be maintained in a single ledger. Those with their announcements will be maintained in a single ledger. And across communities, communities' announcements will be maintained in yet another ledger. In that sense, we are actually reducing the ledger size that can aid in confirmation. Now, something to note actually is that we here use geographical proximity for latency optimization. But if you are to optimize for a trust or for the underlying policies being used in the BGP system, then you might as well consider policies. Moving forward, we actually get rid of the expensive consensus algorithms and utilize a proof of authority-based consensus, which is something that is used by Ethereum. We use the click, the Ethereum click consensus system, and the idea of basically a click is to elect a primary to receive transactions. Here, transactions are basically going to be announcements, BGP announcements of fixes that are reachable from the AES or from that primary, and then order them, compute a block. The block is going to be nothing but a signature on top of a piece of data, and broadcast it to other replicas within the same community, that is within the same set of AESs. And then if you know, the announcement is across AES, then announce it to the neighboring AES within a different community. And so the system makes the assumption that we have identities that are very well known and that very well established. And this is a simple constraint in the sense that the application domain that we have actually have those identities. So AESs have ASNs, AS numbers that are assigned by Erin, and that works just fine. We benefit from utilizing click from the design of a click, which is a low message complexity and delay. Thus this far, and I will talk about that in the upcoming few slides. So a little bit about the how primers are elected in click. The idea is that not everyone actually computes a block in the click. Rather, a single elected primary, calculate basically, back these transactions, order them, compute the block, and broadcast to other replicas. And the option that we go with is a round-robin option, in the sense that, like, say, R1 is elected as a replica, as a primary first to calculate a block. Then the calculation goes to R2, R3, and so forth. And so it's just a standard round-robin fashion, as I mentioned earlier. So what do we have here now? We have basically with the typical design, we have transaction list that is going to be announcements. We will have blocks constructed by the replicas, and we will have a blockchain starting from Genesis that is either stored centrally or in distributed fashion. And so with transactions, it's going to be BGP announcements. With the blocks calculation, it's going to be basically primaries, primary replicas. And with the chain itself is going to be a blockchain or multiple chains. And so a little bit of details about the structure of the transaction itself. The transaction is going to be a very simple ID structure of the replica, and then the ASN number, ID number of the transaction, ASN number of the primary, and then the BGP announcements that are put in the block. And the chain itself is going to look like this. It's going to be basically AS and route, announcements, timestamp, a primary ID, and then the hash a block of n-1. It changed to the block before it. Just a typical blockchain structure. And so click properties. This paper is not really about a click, but and if you're interested, you really will find a lot of resources that are more comprehensive than our work, given click its due right. But the key idea here is that the key guarantees of click is that it would require basically a big O1 message complexity, in the sense that, like, for example, this is the primary. The primary has to basically broadcast a single message in a broadcast fashion to all other nodes in the community. And then it can tolerate F over 2 faulty replicas. That is out of the scope of this work. However, one thing that is really interesting is that in blockchain systems, given delays, what you would have basically is that, say, a given node in the community did not really hear what has been sent, like, failed transmission. And in this case, what we do actually, we treat that kind of failed transmission as double spending. What will happen is that, upon confirming the receiving of the given, say, announcement of the block, basically this will be overwritten, as simple as overruling a soft fork. So as for attacks that this kind of design choice counters, we can see them simply for false advertisements. Routing paths announcements are maintained in a subgroup chain. It's easy to verify whether an announcement is false or not by matching the different transactions. Transaction details, approved announcements are also maintained in a global chain, so cross-community false advertisement resolution would be possible. Partial hijacks treated as double spending, as I mentioned earlier, and the complete hijack is neutralized using the consensus and subgroups. I'll talk about that in the coming few slides. So before I actually go there, I would want to talk a little bit about the delays and its calculations. More details are in the paper. It's easy actually to bound the subgroup consensus time as a linear combination of multiple latencies or delays. And so the subgroup consensus time, TK, can be expressed in terms of the AS to AS latency, AS to AS time, and then the link latency margin. As far as the transaction confirmation time, TA, it's also defined in terms of the in subgroup latency as well as the AS to AS latency with some link latency margin as well. Can be simplified into TV, which is AS to AS time. And then finally, the end-to-end latency can be expressed by the above by combining two qualities. Now, something to keep in mind here is that those determining quantities here are simple peer-to-peer latency, which is on the internet today is in milliseconds. TK, which is above in subgroup latency, is also in milliseconds. TA, which is the confirmation time, is simple digital signature validation, which is also in milliseconds. So we're talking about milliseconds rather than seconds, minutes, or hours. So again, message complexity, if we are to assume that A is the number of ASs and K is the number of subgroups, subgroup size would be the number of ASs over the number of subgroups, that is to say A over K, and the message for confirmation for the number of messages required for confirmation in a click in the overall system can be easily calculated as A plus K square over 2K. So in a practice, when we have about 88,000 ASs on the internet, we can have K, that is the number of subgroups of 211, which is relatively smaller to confirm across than to confirm with individual ASs. So we do a very quick evaluation with simulation to understand the time parameters, just to throw some numbers on the evaluation. And so we make the assumption of the subgroup size as before, the inter-AS round-trip time, just the current latency on the internet between two peers from different ASs. And then we look into the inter-subgroup round-trip time as well using a very simple trace route measurements for different ASs IP addresses and a blockchain verification time using typical digital signature verification. And so the evaluation objective is to understand, we use a real example of the YouTube hijack, and we have the time parameters for the YouTube hijack. What we want to do basically is that we want to see how quickly our system can actually detect a false announcement, and so how that can actually relate to the hijack. And so we want to monitor the damage, compare RouteChain's convergence, and then observe the damage control. And so this is the real example of the YouTube hijack in 2007, in which basically an AS in Pakistan announced reachability of YouTube IP addresses from within Pakistan. So all the traffic of the YouTube, it traveled to that small AS in Pakistan, or ISP in Pakistan. And so around 1847, there was basically like, uninterrupted service. 1847, 45, hijack begins. 48, 9 ASs were hijacked. And then 48, 30, we had 47 ASs hijacked, 93 ASs hijacked by 1849, and so forth. So those are the time parameters, basically. From here to here, there is about 45 seconds, about 1 minute from the start of the non-interruption to the basically the hijack, where 9 ASs were hijacked, and so forth. So you get like the idea that this is about a minute between the no hijack and then the 9 ASs hijacked. So what we had as a result of our simulations, on the x-axis we have the time in milliseconds, that is 80 to 200, that is 0.2, basically 0.2 second. And then what we had on the y-axis is basically the subgroup nodes contributing to the primaries, that is a percentage. So when you have like 10% of the replicas in a given AS group as primaries, potential primaries, up to 100 of them. And so when 100 of them are there, meaning that a larger time is required for consensus between them naturally, what we have observed is that under a partial hijack, what observed is that like you would need about 0.2 seconds to converge. By looking into the complete hijack, that is a complete hijack of the given service, and the route itself, all of it from the source to destination is being under attack, that is hijacked. What we have found is that, again, with the subgroup being, or subgroup primaries being a percentage of the total number of nodes in a given community, what we have found is that to be able to achieve, say, for example, when 50% of them are actually under attack, we will have about 40 seconds, which is a quite short time. So other observations that we make is that we make that RouteChain achieves consensus among the 88,000 and more ASs on the internet today in approximately 0.2 seconds, given that does not really require any heavy computations, rather the latencies on the internet. And within this time, in YouTube attack, less than 9 ASs were compromised or hijacked, and the attack itself could be actually rolled back and mitigated. So in conclusion, we have proposed RouteChain, which is a customization of a generic blockchain system. It's a blockchain-based system to prevent PGP hijacks or address PGP hijacks. It enhances security of ASs, incrementally deployable with legacy systems. More details on this argument is in the paper, and it is promising with results from simulations. With this, I'm very glad to answer any questions.
Thank you. So you can take a few questions. So by the time we take the question answer, I will request the second author to set up the presentation.
So in this case, you knew that it was a YouTube attack, right? So
that was yeah,
a simulation, right?
Yeah.
So how long would it take you to detect an attack that you didn't know about?
So the system that we have here is not to detect attack, but to prevent the attack from in the first place. Meaning that if somebody make a false claim, a false announcement, meaning that I would say you are reachable from me while you are not. Mm-hmm. Others, through their corresponding announcement, have to witness to that, and so this in the first place will be prevented. Okay. So I don't have to go and look into the ledger to find out which is false and which is not. Mm-hmm. And the delay there is just a latency for the calculations that we have to do for that evidence that we post in the ledger.
Right. Thank you.
Sure.
Any other questions? So if not, then let's thank the author. So we have the second paper, BlockONS, blockchain-based object name service. The paper will be presented by Wandek Yu. Wandek is a PhD student at KAIST, Republic of Korea. His research interest is Internet of Things and wireless networks. So over to Wandek.
Hello everyone, I'm the Wandek Yu from the KAIST. Today I introduce about the BlockONS, which is the blockchain-based object name service for the Internet of Things. So the outline is like this. I introduce about what is the Internet of Things and what is the service discovery for the Internet of Things, and the second one is background of the service discovery, and the problem definition and related works, and I introduce my platform. So the Internet of Things vision is brings a lot of virtual service to the person's wants and desire. So we need some special middleware to find the service by using the Internet of Things. So before in the past year, the Internet of Things technology is evolving now. So the first history is there of M2M protocol, which is only collect the data and transmit it to the people over the internet. And second one is to the Internet of Things and people, and connect it to each other to communicate their providing some service. beyond the Internet of Things, we tell it the Internet of Everything, which is thing, people, and the space is intercommunicate with each other over the Internet and creating the new intelligent services. So in this time, we have to we have to connect to this kind of intelligent services to the people's wants and desire. So there are some standard service discovery is indispensable now. So like a web service technology, the service discovery, such as a service engine and search engine for Google, that kind of thing is a play a very key role in the Internet of Everything era. So almost all IoT platform basically provide this kind of service discovery protocol, but the fragmented development of the service discovery is occurred, so it degrades the growth of the IoE now. So due to the need for the integrate the service discovery system, so based on the international standard, fortunately, the global standard 1, which is non-profit international standard organization, standardizes the object name service, which is naming service that provide a way to register and discover and access to the virtual service leveraging the JSON identification standard and DNS protocol. So this is an overview of ONS. So there are some service providers here. He registered their service for their IoE devices. And the service searcher is connected to this kind of DNS-based service discovery infrastructure to find this local ONS. And when the ONS find this local ONS by using the JSON identification, then the server returns the service listed to the service searcher. So the background is, what is the JS1? The JS1 is non-profit international organization that developed and maintained the global standard for the business communication. And they define and standardize the JS1 code, which is used for the global unique identifier of things, or such as a product, location, asset, document, and people, that kind of things. There are 12 types of JSON code for the IoT and product now. And nowadays, the JSON code is up here, the trillion products. You can see every barcode in the product that is defined by the JS1, and almost every product is used this JSON code for the distribution or the providing some service. And moreover, the JSON code is used to identify food, drugs, railway, defense, smart city, and so on. Especially the FDA, the US FDA is forces to use the UDI, which is provided by the JS1 code for the medicine now. So a lot of products and IoT devices use the JSON code for identification. So this ONS system is also used JSON operated based on the JSON code and ONS DNS-based service discovery. So the process of the ONS is very simple. Just scan some barcode or scan this JSON code through the camera or Bluetooth, Wi-Fi, any media. So when the ONS application get this kind of JSON code, they convert this JSON code to some application unique string, and the ONS client make us the DNS query. This is FQDN to discover the local ONS, that store the service of this product. So when the local ONS return the query response, this is a DNS protocol, name authority pointer record. It is standardized by the DNS. So after the ONS client get this kind of a service list, the user can access to the service server through the URL. But the problem is because ONS is operated by leveraging the DNS protocol, so it has several limitations. So, for example, the DNS cache poisoning, or the local DNS cracking, or packet interception, like this kind of attack is influenced on the ONS protocol, ONS server. So there are some problem. What if the service associated thing is tampered or forgery? And what if the local ONS server is broken down by caused by some attacker's attack? So there are two issues: security issue, voluntary of the data tampering attack, such as DNS cache poisoning, spoofing, and local ONS cracking, and availability issues, the weakness on the sustainable service when the local ONS that store the original service data is broken down. So originally the service is stored in the local ONS. So when the local ONS is broken down, the people cannot discover the service which they want. So this is related works. There are some several works for the preventing the local ONS cracking or security and availability issue, and some to protect the tampering attack or service data. But this kind of related work is limited on they only consider about the attacks during the process. They did not consider about the data already is forged by some attacker. So we have to validate that data is all correct or not, and we have to handle the fault tolerance algorithm for fault tolerance mechanism for the sustainable service for the ONS. So our approach is very simple. Just if blockchain has some characteristic, which is the data integrity, and they share all their data through all distributed ledgers. So we use we apply the blockchain to the ONS. So there are this is existing ONS servers. There are lots of local ONS servers now, and we collect some critical data, and we refine the ONS's service data as a refined data, and store it to the blockchain, and use that blockchain data to validate the data tampering, and we use the blockchain to distribute the services and providing strong fault tolerance. So the main purpose is data integrity and sustainable services. So there are some challenges to solving this issue. Then the first one is how to distribute and store the IOE and their service data in the blockchain. When we just store the original IOE data and service data in the blockchain, it is not efficient. So we have to optimize the blockchain database to increase the performance through apply some off-chain scaling. And how to validate the tampering of the service data using the blockchain. I said we stored some critical data in the blockchain. Then after that, how we use that data to validate the original data which is stored in the off-chain. And third one is how to maintain the sustainable service over the blockchain. I said the blockchain has only the refined critical data, so they cannot the service searcher cannot understand the data in the blockchain. So we have to consider about how to connect it between the off-chain database and how to provide the sustainable service using some synchronization and subscriber and synchronization mechanism. This is the overview of a blockchain. I said there are three issues. The first one, one is white box, is meaning the the first one is a gray box. It is meaning the service provider registered their service with the JSON code, and registered service registered service is now they send the service data to the off-chain database, which is called the BlockONS agent, and client is handled that handle the service data with the JSON code and refine that data to by using the critical factor, and that the off-chain send the service data with service data to the BlockONS TP. This is a hyperledger Sawtooth-based blockchain node, and they store the critical data into the global state. After then, when the service searcher want to discover some services, the service request to the service data to the BlockONS agent, and BlockONS is compare the original data, which is stored in the local database, and the global state in the Sawtooth node. So by comparing the original data with some critical data, they can verify the data tampering is occurred or not. And third one is the BlockONS agent is just on off-chain, so they store the original data, but this original data is not shared basically not shared by another BlockONS agent. But for the maintain and keep the service sustainable service, we have to consider about some subscriber and synchronizer process to copy and share their original data to the other agent. So this is the architecture. I say the BlockONS server, which consists of the BlockONS node and agent. BlockONS node is a blockchain node for the storing critical data. And then BlockONS agent is just kind of off-chain, and is a preprocessor for the blockchain node. And this is optimizing the transaction and refine the data before the accessing the blockchain node on-chain. And Sawtooth network is we use hyperledger Sawtooth project to implement our project. And BlockONS user is there are some two row service provider who is provide their service, and service searcher is who is discover the service what they want. And in terms of everything is here. This one is there are some smart city or factory, that kind of all of the internal things connected to some service point, which is physical cognitive domains, barcode, QR code, that kind of things. And ONS application read this kind of service point to get us some JSON code to find the service and discover the provider discovering the services. So first one is optimize the blockchain performance through the off-chain scaling. I said we applied some off-chain scaling schemes to increase the performance of the blockchain. So the BlockONS agent off-chain is a preprocessor for the blockchain node, and it is optimizing transaction and refining data before accessing the on-chain. And blockchain node on-chain, they just refine the critical data in the global state. So the first one is we defined the new service data model, because the left side one is original ONS service data. This is a ONS service data model, NAPTL record and service type XML, but we have to redefine this kind of this service model to the off-chain service data model and on-chain service data model. So redefine by redefining the service data model, and we use this service data model on the off-chain and on-chain. The second one is we have to refine the off-chain data into the on-chain data, reduce the size of data, and ensuring the collision resistance. So if we use the hash algorithm to reduce the arbitrary size of the original data to the fixed size of critical data, and we also ensure the collision resistance. So I said this original data is mapped to the refined data, and the hash value must be the change. The refined data is hash value, and hash value must be changed when the original data is changed. So this feature will be used to verify that the original data is tampering or not. And we also consider about how to distribute the obtained service data efficiently with the sustainable services. So we define the three types of agent off-chain data, off-chain node. So the full node is they store the data and they provide the discovery data, and they also there are distribution synchronization rules, the copy and share. So when the full load is existed in the BlockONS system, they automatically share their own service data to the other off-chain to provide the sustainable services. So so we also and second one is service data validation method. I said to compare the hashed off-chain data with the on-chain hash data. If they're same, the data is secured, and if they different, the data is tempered. It's a very simple algorithm. It's just when the service provider and service searcher is recast the service data from the off-chain, the off-chain is automatically access to the BlockONS node to check the hash of data by using the local DB and the hash of data in the global state in the blockchain. So by comparing two hash of data, we can know the data is secure or tampered. And for tolerance mechanism, I said there are role-based off-chain model provide sharing and copy original data to other agent, and this agent information is also stored in the blockchain. So we can find when the sum of the off-chain database is no longer working caused by some broken down or fails, the service searcher blockchain client will access to the on-chain data, on-chain pool to find the service data which is copied by the synchronization and subscriber process. So we can find another off-chain which store the service data from this agent. So by using this process, the user can continuously find continuously discover the services which they want. So this is our performance evaluation. This is an evaluation environment. We use the Intel Luke and the network by using the Wi-Fi network to construct the blockchain node and blockchain off-chain and on-chain node. So the result is if the off-chain scale, this is the off-chain scaling performance improvement. So the blockchain ONS could save the 76% of the RAM throughout the off-chain scaling. I said we reduced the size of the original data to critical data. By using the hash algorithm, we can reduce the data size in the global state. Global state is kind of database in the hyperledger sawtooth. So by reducing the size of the global state, the service provider could reduce the operating cost because the RAM is very expensive. So the second one is this is a service registration and discovery performance. There are two types of service data in our BlockONS. The first one is service data, and the second one is the description of service data. So we experiment about the two types of service data. So this one is registration evaluation. Comparing with the original ONS, it shows around 10% of the performance increment. So this is a result. This is conclusion. The BlockONS provide the secure and reliable service management and discovery system for the Internet of Everything, and we use the hash-based data validation method for the security, and we also defined some hash and role-based off-chain scaling and subscriber and synchronizer-based tolerance mechanism for the availability. Thank you.
Thanks, Mandu. We can take a question. Okay, so I have one question. Like you have used the sawtooth consensus, right? Any specific reason for using sawtooth?
Because sawtooth provide, compared to other hyperledger projects, sawtooth provide very flexible implementation for the business logic. So because we choose sawtooth is we have to modify the consensus, and we have to codify some smart contracts for the providing our services. So
but it requires some special hardware like SGX.
But sawtooth also provides some simulator for their consensus algorithm. So we don't have to special some hardware for the experiment. But if we use that kind of special hardware, we can get a more performance than compared to this kind of results.
Thank you. So the third and the last paper of this session is Trinity, a Byzantine fault-tolerant distributed public subscribe system with immutable blockchain-based persistence. This paper will be presented by Dr. Gauri Shankar Ramchandran from University of Southern California. So Gauri is a postdoctoral researcher at Cyber Physical System and Internet of Things, Viterbi School of Engineering at University of California. His research interests are IoT, smart cities, edge computing, and network protocols. Lately, Gauri is exploring blockchain technology and its application in IoT. He received his PhD from KU Leuven, Belgium. So over to Gauri.
Test. Thanks, Sandeep, for the introduction. Good morning, everyone. So I'm going to present Trinity, which is, to the best of our knowledge, is the first distributed publish subscribe broker. So this work would not have been possible without the support of my colleagues. So I would like to take this opportunity to thank Kwame Wright, Lee Cheng Zheng, Pavas Navni, Mohammad Naveed, Jagjit Daliwal, and Bhaskar Krishnamachari. So I'm going to follow this outline today. So before I move on to our proposed distributed publish subscribe broker, I'll provide an introduction to this publish subscribe communication pattern. Then I will explain why we need to distribute this publish subscribe broker. Then I will go into the details of Trinity, and we also did some implementation and evaluation. So I'll present some of the key results. And lastly, we are also applying Trinity to one of the real-world applications. So I'm going to talk about the application as well before concluding my talk. So, okay, let me start with the introduction to the publish-subscribe broker. So many of you may be familiar with the publish-subscribe communication model. So it is widely used in a number of applications. So it follows client-server architecture where you have a broker, which is this centralized entity, which is typically hosted on a server. A number of clients, which are either publishers or subscribers, they connect to this broker to exchange data with each other. So publishers here refers to the data producers, so they are the one producing data, and they relay their messages to the broker following a concept called topic. So each message is tagged with, let's say, human readable string. That's what they call it as topic in this context. And as a subscriber, if you are interested in reading the data or consuming the data, you would request the broker to forward the messages whenever a message is published at a certain topic. So that is sort of the high-level overview of Trinity. So the key building blocks, I want to emphasize it here because it's going to be important for the later slides. So broker, publishers, and subscribers are the key building blocks of Trinity. And also one of the benefits of using publish subscribe broker is it isolates the data producers from the data consumers. So as a data producer, you don't necessarily know who is consuming your data. So it sort of provides this complete isolation. And also it provides one-to-many message distribution, which means that one producer can actually share the data with the multiple consumers or subscribers. So this is sort of the high-level overview of the publish-subscribe communication pattern, and it's widely used in a number of real-world applications. So you can see some of those applications here. I mean, this is not a complete list for sure. I mean, there are a wide array of applications that you can find in the internet. So I'll go into the problems that we are solving in the context of this work. So, I mean, as you have seen in my introductory slide, that the publish-subscribe brokers are centralized in nature, and today's pub-sub systems typically trust the broker owners. And I mean, centralized solutions are working as long as you follow this trust model. But then it also leads to the central point of failure. So the organization that owns and manages the brokers, they could actually tamper with the data, or they may manipulate or withhold the data. So therefore, this centralized model is susceptible to Byzantine failures. So I mean, you cannot completely trust the organization that owns the broker in some application cases. So because of that reason, we probably need to come up with a solution that can handle Byzantine behaviors. And also there's no reliable persistence mechanism in our traditional publish-subscribe broker. But if you look at many of the real-world applications, I don't know how many of you have attended the tutorial sessions yesterday. So we repeatedly hear about the supply chain use cases and the number of stakeholders involved in the supply chain use cases. So if you look at many real-world applications, you typically encounter various stakeholders who has some sort of a stake in the application. So for example, here I have an application which again comes from the supply chain domain, where you have the food producer at one end and the consumer at the other end. And the food products, they typically move through multiple stakeholders' infrastructure, which includes storage units and processing unit and whatnot. So when the food products move through these different organizations, let's say that you are interested in making sure that the food product is maintained at the right temperature, humidity, and so on, and also you want to keep an eye on the expiry date. Because the reason why you want to keep track of all this information is when there is a problem. I mean, we heard yesterday in the supply chain use case that in some cases it was difficult to find out which stakeholder actually made a mistake or poorly handled the food product. So in such cases, the right way of storing and managing information is highly necessary. If you follow the centralized communication model, that is a centralized broker, the organization that owns the broker have the complete control of the infrastructure. If there is a problem, let's say if there is a outbreak due to some food product, or if there is a financial loss and all those things, you need to find out which entity in the supply chain created that problem. If you follow the centralized model, there is a possibility that the entity that committed a mistake, they may collude with the broker owner and misrepresent or mishandle or tamper with the data to hide the truth from being visible. So that is sort of the problem in the centralized model. But if you have a distributed model, you can actually have all these organizations play a key role in the handling of information. So that is where we are heading with Trinity. So if you, this is what we want to solve, but then what is already out there? So if you look at the state of the art in this PubSub broker space, you have Apache Kafka, which is a centralized broker. These brokers can handle fault tolerance, but it cannot handle Byzantine fault tolerant. And the other brokers are MQTT, ZeroMQ, PubNub is also a company that is providing PubSub service. All these brokers can deliver messages to different parties, but these are all centralized. So if you look at this table, none of the contemporary brokers that you find today are not capable of handling Byzantine failures. They can handle crash tolerant, but they cannot handle Byzantine failures. That is, a single organization is always owning and managing the broker in all these model. So this is where Trinity comes into picture. So Trinity is a Byzantine fault tolerant distributed publish subscribe broker. So sort of the high level overview of Trinity. So Trinity allows the brokers to be owned and managed by different organizations, and this can be hosted either on-premise or on the cloud. And it guarantees that all the subscribers see the same verified stream in order. Let's say that there is a publisher or a data producer sends a message to the broker. If you're subscribing to that message from one of the brokers, you can be guaranteed that all the subscribers that are part of this Trinity infrastructure would see the same message. Why is it important? Because you don't want a different entity to be seeing different messages to hide the truth. So that is sort of the model that we are going for. The way we achieve this is by integrating the broker system with the Byzantine fault tolerant consensus protocol and distributed ledger technologies. So this is sort of the system model of Trinity that we follow. We consider multiple domains. So here are the set of domains in the slide. And each domain consists of a broker and a collection of publishers and subscribers, and then a consensus node that is responsible for achieving consensus. So a domain is considered to be faulty if either a consensus node or a broker exhibit Byzantine behavior. And we also make an assumption that the correct consensus nodes and broker nodes are considered to be online to handle the messages that are produced by the publishers. And also, of course, the publishers and subscribe clients are assumed to be correct as well, and they are non-faulty and are part of the non-faulty domain. So these are the key assumptions that we make, and if you look at this diagram, we consider multiple domains, and this is a broker layer which just handles the messages that comes from the publisher. And this is the consensus layer, which is responsible for achieving consensus on messages that hits the broker. Whenever a message hits a particular broker, it is immediately sent to the consensus node, and a consensus is achieved on that message before it is relayed to the subscribers who are interested in that message. So that is sort of the runtime behavior of Trinity. So we do prove a number of safety and liveness properties of Trinity to guarantee that our broker is actually capable of handling Byzantine behaviors. Just to give you a quick overview, that safety in this context means that something bad will never happen, so we need to ensure this property. And liveness here refers to something good eventually happens. So these are the two properties that we are trying to prove for Trinity here to ensure that it is capable of handling Byzantine behaviors. Again, due to the limited time we have, I'm not going into the details of all the safety and liveness properties. So I would encourage you to read our paper to get a better understanding of some of the properties. So one of the properties that we prove in the paper is publisher safety, which states that all correct publishers can guarantee that all their messages are delivered to all correct subscribers. And to prove this property, we have given a number of definitions and assumptions in the paper. So I'm going to highlight some of them here as I talk about this proof. So I already mentioned that a correct publisher by definition is assumed to be in the correct domain. Therefore, the messages produced by the publisher is actually trustworthy. Therefore, its messages are actually delivered to the consensus layer without being manipulated or mishandled in the process. And also the consensus layer guarantees reliable consensus on the messages as long as 2/3 of the nodes in the network are reliable and trustworthy, because we follow the Byzantine fault-tolerant consensus model, which states that as long as 2/3 of the consensus nodes are non-faulty, we can guarantee that the messages are actually properly validated by the consensus nodes. And also it states that the correct subscriber, as long as these processes are handled correctly, the correct subscriber will hear this delivered message. So these are the other assumptions that we make. I'm gonna refer you to our paper to actually go through the proofs in better details. And in addition to the previous safety property, we do have a couple of other safety properties which are defined in our paper. And here I'm talking about one of the liveless properties that we prove in that paper, that the messages from any correct publishers are delivered to correct subscribers within a bounded delay. And to prove this property, we already mentioned that the correct publishers are already assumed to be online to send their messages. And when the messages hits the broker forwards these messages to the consensus node within a finite amount of delay. And then this consensus nodes would deliver the messages to all the other consensus or validated nodes in the network, as long as the majority of the consensus nodes are non-faulty in the network. In a nutshell, what we are trying to prove is that as long as all the publishers, broker, and the consensus node are non-faulty, the subscribers are guaranteed to receive the right message within a bounded delay or within a finite delay. So that is sort of the liveness property that we are proving. What happened? Yeah. So that's sort of the high-level overview of the liveness property. Again, due to the limited time we have, I'm unable to get into the details of all the properties. So I would highly encourage you to read our paper to better understand some of these properties and proofs. So we did implement Trinity on a real consensus, using a real blockchain platform. So in this case, we relied heavily on Tendermint BFT, which is one of the well-known and easy-to-use blockchain platforms out there. So we use that as a key evaluation platform. And for your information, the Cosmos is actually built on top of Tendermint BFT. So which is one of the well-constructed blockchain platform. And we actually managed to run Tendermint BFT on Raspberry Pi nodes, so which is also another interesting thing that we discovered in the process. So our evaluation was carried out on a 20-node Raspberry Pi testbed. To implement Trinity, as I mentioned, that the contemporary brokers are not capable of handling Byzantine behaviors. Therefore, we extended the MQTT broker with support for handling Byzantine behavior. So our architecture is platform agnostic. So here you can see a sort of our architecture figure in the diagram. At one end you have a broker. At the broker, we sort of expose a collection of APIs which you can use to interface with the blockchain platform that you want to use. So in this case, the blockchain platform that you want to use, they provide a client library. So all you need to do is you need to connect your Trinity APIs with the blockchain library to create this distributed PubSub broker with Byzantine fault tolerance. So our architecture is agnostic to the underlying blockchain platform itself, and that is one of the key design decisions that we actually went with when we were designing the architecture of Trinity. So that is sort of the high-level overview, and those who want to check our implementation and want to try out Trinity, you can go to our open source implementation of Trinity that you can find at the link there at the slide. So, I mean, again, due to the limited time we have, I'm not going to go into the details of all the evaluation that we did. Some of the key results is, I mean, traditionally, the publish-subscribe brokers are centralized, which means when a publisher sends a message to a broker, the broker immediately checks if there are any parties interested in consuming that message. If there are any parties, then the messages are delivered to those parties. So it is so simple, and there is no consensus, there is no verification, or there's no heavy processes in this channel. But now we are introducing this consensus to actually provide Byzantine fault tolerance, and also to ensure that all the subscribers in the system are actually seeing the same message. We are introducing this additional consensus process to this publish subscribe channel. And this process sort of adds a delay of about 3.5 seconds when we used 20 nodes with 5 transactions per second. And again, when we use 20 nodes, we actually needed to have 2/3 out of those 20 need to actually approve the messages to have the Byzantine fault tolerant consensus. And because of the number of validators involved in the consensus process, and also the processing overhead of the Tendermint BFT consensus algorithm, the end-to-end delay for our publish-subscribe communication was roughly about 3.5 seconds. And if we use centralized broker like we do today, it takes about less than 100 milliseconds for a message. So as you can see that the centralized broker is really fast, but it cannot provide you Byzantine fault tolerance. The messages that you see may or may not be the truthful representation of the reality. So again, I want to note that, of course, we are adding a slight delay to this consensus process. But again, we are getting this Byzantine fault tolerance capability in response to that. So again, we did some evaluation on Hyperledger Fabric. Again, because of the solo consensus, it was much faster there. And again, we used Hyperledger Fabric only to show that our platform is actually agnostic to the underlying blockchain technology. And some of the other key results, again, if you use this with other blockchain platforms, you will the end-to-end delay is actually a function of how the consensus is achieved on those blockchain platforms. And it also introduces some significant overhead if you're doing consensus, because each message that gets sent to the broker has to be relayed to all the consensus nodes in the system. Therefore, the higher the number of validators in your network, the higher the network overhead here. And we also noticed some significant network and CPU usage. We do have immutable storage of data that comes from the blockchain platform itself. So in this version of the paper, we haven't delved into the details of our immutable storage or how the data can be retrieved if you want to look at what happened or for auditing purposes in the future. So that sort of concludes my evaluation part. Before I conclude my talk, I'll quickly talk about the real-world application of Trinity. So we are currently applying Trinity to one of the real world use cases with the County of Los Angeles. So they have this requirement that Racial and Identity Profiling Act is trying to prevent unjust practice when they are performing profiling. So profiling happens whenever a law enforcement officer stop a person without evidence to check. And there is the problem in the US that it is not done in a fair manner, that they are actually targeting a people of certain race, religion, ethnicity, and so on. So they wanted to prevent this problem. They wanted to have a fair racial profiling process. Therefore, this Racial and Identity Profiling Act is trying to address this problem. And in one of the meetings last year, the board that keeps track of this particular process, they raised a concern about the data integrity, saying that the police departments are not reliably presenting the information to the Department of Justice. So there was a complaint, or there was a concern that they are selectively picking a collection of data points and presenting that to the Department of Justice to show that there is a fair distribution, but in reality, there was actually not a fair distribution of racial profiling there. So to address this problem, we are actually currently developing a version of Trinity that works with Tendermint, Hyperledger Fabric. And here in this model, we assume that the Department of Justice owns the order or node, because they are sort of the trustworthy organization, and each police departments can run their own local nodes, and the messages from their neighborhood would actually get reported to that local broker, and in turn gets to their peer. So this is again the work at the early stages. We are currently implementing this to test it out in real environment. So that sort of brings me to the conclusion of my presentation. As I mentioned, contemporary publish subscribe brokers are centralized, and they don't provide support for Byzantine fault tolerance behavior. And to the best of our knowledge, Trinity is the first distributed publish subscribe broker with Byzantine fault tolerance capabilities. And we also presented safety and liveness properties in the paper to prove that we are actually guaranteeing this Byzantine fault tolerance capabilities. And the evaluation result shows that the broker adds a delay to this publish subscribe channel, but then it provides this additional level of trust and data integrity for the applications. And we are also applying Trinity to the real world application, which also shows that there is actually a number of real world use cases where such a system can be beneficial. Okay, that concludes my talk, so I'd be happy to take questions now.
Maybe because you use the fault Byzantine fault tolerance. So right now it is 3.5 TPS. So maybe you have analyzed why the performance is so low in each layers. The parallax.
You mean looking at the different layers, as in the consensus and the storage and stuff? Yeah. Yes and no. I mean, we looked into the performance, and one of the reasons is the way we configured our evaluation platform that we noticed is we could get a better result by configuring it in a different manner. But though at the time of evaluation, we felt that this was sort of a fair representation. So how often you produce blocks is actually one of the key factors in this evaluation results. So if you produce blocks very often, you're actually reducing the consensus by a small margin. But again, you're not actually solving the problem. This is, I believe, is a true representation of the end-to-end delay. We could probably do that better with a better configuration or a much faster consensus algorithm.
Yeah, you talk about the consensus algorithm. So go ahead. If you are right now, migrating there to the hyperledger fabric, right? It is actually not the Byzantine fault tolerance,
Of
right?
course,
So
yeah.
what's your plan? You're gonna implement the
Yeah,
consensus
so like I
model?
said, I even mentioned in the slide that the reason why we did it with Hyperledger Fabric is to show that the platform is agnostic to the underlying blockchain platform, and that's why I mentioned that we use solo consensus, which is actually not a Byzantine fault tolerance, which is again sort of a centralized consensus model. But we just showed that it is possible to use different platforms, but you know that there are different variants of Hyperledger that that provides different capabilities. So going forward with this implementation guidelines, they can extend Trinity with different blockchain platforms. That is sort of the idea here. But again, we don't strongly recommend using Hyperledger Fabric as the platform for achieving this Byzantine fault tolerance. Let me make that clear.
Thank you.
See, the idea of replication existed much before blockchain. The idea of BFT was there before blockchains. And here, I don't even see the reason for blockchain. You could have just used BFT, except for the last application in DOAJ where they wanted. Otherwise, the application can be done independent of blockchain. So why blockchain?
That's a very good question, and that was also one of the surprising thing for us. When we did a literature survey on this particular topic, we couldn't actually find any platform, any published subscribe broker with Byzantine fault tolerance capabilities. All the platforms that we have provides replication, but again, replication does not strongly recommend that the brokers are actually owned and managed by different organizations. They don't strongly make that recommendation in any of the standards in the broker implementations. There was just one paper which presented the possibility of doing Byzantine fault tolerance PubSub broker, but surprisingly, I don't know, given the number of literature we have on BFT consensus and so on, none of the papers actually address this problem. And yeah, we just bumped into the problem. Your question on why blockchain. Again, we wanted to build a Byzantine fault tolerance PubSub system with some sort of immutable guarantee. And this is coming as like a given on blockchain platform. You have both the Byzantine fault tolerant consensus and also the capability to persist information in a reliable fashion. Therefore, it was much easier to actually build using a blockchain platform. But you're absolutely right. We could definitely build it by just picking a consensus from somewhere and then another immutable storage mechanism from somewhere. But again, the flip side, that would actually lead us to a blockchain platform of some kind. So I think that's one of the reasons why we actually went with this approach. But as you can see, that almost all the blockchain platforms provide the APIs and the capabilities to actually build such a broker. I mean, and also for practical reasons, it is much easier to go with the blockchain platform, given the amount of developer movement we have these days. One can actually quickly adopt this architecture and build their own version of distributed broker.
Thank you.
So maybe due to the interest of times, I see there are other questions. We can take it offline during the tea break that we have. So thanks, Gauri, for the nice presentation.
Thank you.